Hello, so in today's video, we're going to look at proof by contradiction. So let's just describe what proof by contradiction means. So proof by contradiction is when you want to prove a mathematical statement is true by assuming that the contrary statement is true. So assuming that the opposite statement is true to the statement in the question, and then performing some calculations to arrive at a conclusion, which is a contradiction that contradicts your initial assumption. Really, I should have written the word conclusion here. That's what I really meant by that word there. Let me just change this to conclusion. So we want to arrive at a conclusion after performing these calculations that contradicts the initial assumption, the contrary assumption that we made. So basically, what we want to do, I mean, I'll go for an example, this first example here. This is the example we're going to focus on in today's video, the proof that root 3 is an irrational number. So to prove this statement, we're actually going to assume that root 3 is actually a rational number. And then we're going to perform some calculations. We're going to get a conclusion from those calculations. And that conclusion is going to contradict the initial statement that root 3 is rational. And if you've got two statements to contradict each other, then that must mean the initial assumption is not correct. So that must mean that root 3 is actually irrational. So remember, a rational number, let's just go through a summary of this. So a rational number, just to remind you, a rational number, for example, x in the set of rational numbers, so this Q notation. So this is a number, that can be expressed, so a number that can be expressed in the form x equals n over m, where n and m are integers, so m and n are whole numbers, integers, such that n and m are co-prime. So again, this word co-prime, what this word co-prime means is it means that the highest common factor between n and m is 1. So in other words, a rational number is a number that you can write as a fraction with an integer divided by an integer, where you can simplify the fraction again into an integer over an integer. So what I'm just saying here is that this fraction n over m is the simplified fraction. So for example, the number a half is a rational number. So as an example, if x was equal to a half, that's a rational number. Obviously, you can write a half as the same as 2 over 4. You can obviously write a half as 2 over 4, and you can obviously write it as 3 over 6, and so on and so on. So I'm just saying that a rational number is a number that you can write as a fraction in its simplest form with an integer on the top and an integer in the bottom. So 1 and 2 are both co-prime. 2 and 4, these are not co-prime. So 2, 4, not co-prime. But 1 and 2 are co-prime. So 1, 2 are, they are co-prime. Sorry, let me get rid of that. They are co-prime. So they're numbers, two numbers that have a highest, a greatest common factor, highest common factor of 1. And obviously 3 and 6 are also not co-prime as well. 3 and 6, not co-prime, because they have a highest common factor of 3. Okay, so that's just a summary of what rational numbers are. So going back to the question, we want to prove that root 3 is an irrational number. So how would we prove root 3 is irrational? So it's a proof by contradiction example. So what we're going to do, let's just make a note that this is proof by contradiction. Proof by contradiction. So we're going to assume to the contrary. So assume to the contrary that root 3 is actually rational. So we're going to assume that root 3 is a rational number. So let's think about what this means. So we know that root 3, let's just do a bit of like scratch work over here. So we know that root 3 is between root 1 and root 4, obviously, because square root of 4 is 2. Obviously 4 is bigger than 3, 3 is bigger than 1, so we know that that must be true. We know that the square root of 1 is 1, and we know that square root of 4 is 2. So we know that what root 3 is a number between 1 and 2. So we're just going to make a note of that. So we know that we're going to assume root 3 is actually a rational number. So therefore that means that root 3 can be expressed as a over b. So again, a fraction. It's just like what we said here with this x, which we could write as n over m. I'm just going to use A and B as my letters here, but of course you can use any letter you like. N and M would be fine. X and Y, I mean, as long as you have two letters. So root 3 is equal to this fraction A over B, where A and B are integers. So this Z notation, remember that means integers. So A and B are integers. B obviously cannot be equal to 0 because obviously you can't have a number divided by 0 because that's undefined. So B is not equal to 0. Sorry, let me just get rid of that. B is not equal to 0. Now we know that root 3 is positive. We can see that over here by our calculation here in red. So we know root 3 is going to be a positive number. So that means let's just assume that A and B are both positive. So also let's just assume they're both positive. Obviously, a positive number divided by a positive number gets you a positive number. If one of those numbers were negative, then obviously that would give us a negative root 3. That's not allowed because we know from the calculation here that root 3 is a positive number. So we're going to assume that A and B are both positive integers bigger than 0. So they're both positive integers bigger than 0. That's what we're going to assume because because we know that root 3 is a positive number. So assume that they're both integers, whole numbers bigger than 0. You could assume they're both negative because, again, if you do a negative number divided by a negative number, you get a positive number as well. But I'm just going to assume they're both positive because a positive divided by a positive is positive, and it doesn't matter whether we assume they're both positive or both negative. So let's just assume that. So therefore, then, what we can do to both sides of this equation is we can square both sides. So we get 3 is equal to a squared over b squared. Okay, so from that, then, what that tells us is that 3 is equal to b squared. Sorry, 3b squared is equal to a squared. Okay, so what is that telling us? So what does that tell us? So it tells us that a squared must be a multiple of 3. So b is a whole number. So that means b squared is a whole number. A whole number times by the number 3 is obviously a number in the 3 times tables. Any whole number times by 3 is going to be a whole number in the 3 times tables. This must be a multiple of 3. So therefore, a squared is a multiple of 3. I'm also sorry, I forgot to say something as well. We also want to assume that A and B are co-prime. So assume that A and B are co-prime. So again, co-prime just means if two numbers are co-prime, that means the highest common factor is 1. So it means that this fraction there is the simplified fraction. You can't simplify this fraction anymore. We're going to assume that. So assume that A and B are co-prime. So fraction A over B cannot be simplified. And we can assume that because, again, any rational number can be simplified into a simplified fraction. Pick any fraction you like. Any fraction could be simplified into a simplified fraction. Pick like 2 over 4. That can be simplified to a half. Pick 1 over 3. I mean, that is the simplified fraction itself. So we're just saying, yeah, let's just assume that this root 3 equals A over B, and A and B are literally the simplified. This is the simplified fraction there. So again, yeah, we square both sides of the equations, get 3 equals a squared over b squared, times both sides by b squared, 3b squared equals a squared. So therefore, a squared is a multiple of 3. A squared must be a multiple of 3. Now, a is a positive whole number. We've assumed that it's an integer bigger than 0. Positive whole number. So you've got a square number. So a squared must be a square number. So therefore, a squared is a positive. Well, it's a square number. I mean, all square numbers are positive. So it's a square number, and it's a multiple of 3. So it's a multiple of 3, it's a square number. So every square number that's a multiple of 3, if we think about our list of square numbers, you've got 1, you've got 4, you've got 9, that's multiple of 3. You've got 16, 25, 36, that's a multiple of 3, 36. So every square number, when you square root it, you also get a multiple of 3 as well, because you've got a number which is a squared, which is literally just a times a. So a times a is a multiple of 3. So that means one of those numbers must be a multiple of 3, but a times a is a times a, so they both must be a multiple of 3. So therefore a itself is a multiple of 3. So a is a multiple of 3 as well. Okay, so we know that a is a multiple of 3. So therefore what that means, so what does that mean? So that means that therefore we can write a as 3 times an integer n, where n is a positive integer. And I just put a plus sign up there to make it clear that n is a positive integer. So again, if a is a multiple of 3, then it means that you can find another integer n such that 3 times that integer gives you a, because a is a multiple of 3. So we know that for a fact. Now we're just going to plug this into our formula up here. I'll plug this into, I'll call this star there. So substitute our result, substitute into star. So if we do that, we get 3b squared, so 3b squared equals a squared, which is going to be 3n all squared, which is equal to 9n squared. Now what we're going to do now, so we got basically 3b squared is equal to 9n squared. We're going to divide both sides by 3. So we get b squared equals 3n squared. So what does that imply? So that tells us again that b squared must be a multiple of 3. So b squared is a multiple of 3. So again, using this logic that we used here, you've got a square number. B is a positive whole number. It must be a square number because b squared's a square number. So when you square root a square number that's a multiple of 3, that means that b is also a multiple of 3. So b is a multiple of 3. So that means that we can write b as 3 times, let's say, m, another integer. So therefore b equals sorry, let me just move this 3 there across to sorry, let me just move that across to over here, multiple of 3. There we go. Down there. So then, yeah, so that means that b can be written in the form 3 times m, where again, m is a positive integer. But this is a contradiction. So this is a contradiction because we've got a is a multiple of 3. So that means a is a multiple of 3, obviously. But we've got b is a multiple of 3. We've got root 3 equals to 3n, this here, divided by 3m. Yet we can simplify this fraction even further. So this is a contradiction. So we have a contradiction because we assumed that a and b are co-prime. So we assumed that a over b is the simplified fraction already. This is a contradiction. So again, because we assumed this fraction there was our simplified fraction, but we've got we've basically shown that both a and b are multiples of 3. That means we can simplify the fraction even further. So that's a contradiction. So therefore our assumption cannot be true. So therefore root 3 must be irrational. Because we assumed to do this calculation there, we assume that it's rational. So that assumption can't be true because we've got a contradictory statement at the end here, which contradicts our initial assumption. So the initial assumption can't be true. So therefore, root 3 must be an irrational number. So that's how you would prove that root 3 is irrational. And the proof for proving something like root 2 is irrational or root 3 is irrational is exactly the same proof, but instead of multiples of 3, here you'd get a multiple of 2 or a multiple of 7, or if you had to prove that root 11 was irrational, you get a multiple of 11 here instead and a multiple of 11 here instead as well. So yeah, it's the same proof when you want to prove that the roots of a for example, a root of a prime number. To do that again, you would do the same process. You would arrive at the conclusion that your numerator is a multiple of that prime number and b is a multiple of that prime number, which would be contradictory to your initial assumption that root 3 can be written as a rational number, as a fraction in its simplified form. So that concludes today's video about proving that root 3 is irrational. In the next video, we're actually going to prove that there are infinitely many prime numbers, also using proof by contradiction. So that's going to be the next video.